Marco Dentz from the, I hope that's the first one, maybe from the Institute of Environmental Assessment and Water Research, maybe, because I was just spontaneously asking if I can session. And then I think you can start already. The process is yours.
Thank you. Thank you. Thank you for the presentation. So I'm going to talk about transport upscaling in heterogeneous porous fractured media. So afterwards we will have another talk about fractured media by Philippe David. He will probably say everything wrong that Marco just presented. But let's start. This is the outline for the next 3 hours. We are first going to talk a little bit about flow, say phenomenology and of flow transport in porous media, motivation. Then I'm going to talk about the dispersion principle as the classical upscaling, say paradigm. Then about situations beyond this dispersion principle where this does not work. And then explain what are the mechanisms that lead to phenomena that cannot be described by dispersion. Then I'm going to introduce 2 models. Actually, it's one model that can be that can be split in 2 different phenomenologies. And then I'm giving simply some examples of upscaling exercises from the pore to the regional scale. And then in the end, some applications, or say further extensions of these frameworks that I'm going to present you for the quantification of dispersion of bacteria on the pore scale, and then for dispersion in nonlinear flows, for example, non-Newtonian flows or turbulent flows. Okay, so, good, that direction. Motivation, maybe motivation I don't have to say much. Yeah? So why are we looking at porous media? Many things, groundwater management, soil remediation, hydrogen storage, other industrial, environmental applications, carbon dioxide storage. You have heard presentations about these things during the last 2 weeks. Geothermal, nuclear waste, hydrocarbon production, etc., etc. But also in other contexts, porous media are very important. For example, in biological media, for chromatography, catalyzers, batteries. There are many, many applications in which one wants to upscale processes from the pore to the continuum or continuum to regional scale. And I probably don't have to say much about this either. We are talking about porous media. So here I'm just showing you 4 examples of geological porous media on different scales. It's a multi-scale problem. We have heterogeneities on the millimeter scale or micrometer scale, on the scale of pores. So this is a sandstone. It's an XMT image. And on the top you have, say, photos or images of the real media, and below you have the computational abstraction that we make. Now, if we want to simulate flow and transport. So here, this is, let's say, digitally reconstructed barrier sandstone that is reconstructed from an X-ray microtomography image. So here we have a gravel sand-like medium, and this is the, let's say, the standard model of hydrogeology is a multi-log normally distributed hydraulic conductivity field. This is what you see here. So if you would sample the values of conductivity here, you would get a log normal distribution, and multi-log normal means that they are correlated. Yeah? So here we have fractured rock. I think this is from the Costa Brava in Spain. And this is a DFN, discrete fracture network, that was constructed by my colleague Jeffrey Hyman using a DFN works. We have also seen a few presentations where DFN works was used. And then finally here we have a cast network. That's so here on the hundreds of meter scales, but cast networks, they can be kilometers. I think the longest is 250 kilometers. I think somewhere in the US. And this is a very simple representation of it is simply a network that contains nodes and conduits. Yeah? Good. So, in principle, the equations that govern the flow in porous media, they are normally relatively simple. Now, if we look at laminar flow, linear flow, we use the Stokes equation. I think Tomáš introduced another Stokes equation. Maybe he also did the simplification to Stokes. This is for flows in which the Reynolds numbers are very low. These are typical situations that we have in geological porous media. There can also be situations where you have turbulent flow in porous media. In industrial applications, or if you have a big pore space, or if you have cast networks, for example, there you have very high Reynolds numbers. But of course, the conduit size can be meters. No? And in a porous medium, we are talking about hundreds of micrometers lengths and widths of conduits. But so the equation is very simple. It's a linear equation, and but the complexity comes due to the structure. No? So there can be big contrast in the pore diameters. No? You can have, I don't know, 2-3 orders of magnitude of difference, and this is what makes the flow interesting. So you can have regions of high flow, you can have regions of very low flow velocities, and all of this is impacting on the transport. So then, here we already encountered the first example of upscaling, namely for the flow. No? So if you would need to solve, if you want to do a reservoir scale simulation, if you want to solve the Stokes equation and characterize your porous media on a millimeter scale, is absolutely not possible. Not even with the biggest supercomputer. No? And this was recognized by people maybe 200 years ago, by Darcy. And he didn't have a supercomputer, but he just wanted to understand how the flow works. No? Let's say there are different motivations why one wants to do upscaling. One is, from our point of view now, a computational requirement. The other is maybe you want to understand how the system works, and you want to come up with a simple law to describe it. And this was the Darcy law. I think you all know this. Of law, the discharge is equal to hydraulic conductivity times the head gradient. And here the heterogeneity comes because you may have different materials of different grain sizes, different geometry that contribute to a variability of hydraulic conductivity. So this is the solution of the Darcy equation in this multi-log normally distributed K field. And then you see you have a complex flow network. So these are flow velocities that you see here. Blue is low and red is high flow velocity. So you have regions or you have islands of small, and you have more or less connected regions at intermediate and high velocities. And then here we have a fracture network, similar properties. So the flow equation is even, let's say, is even simpler than Stokes or Darcy. It's a Reynolds equation where you relate the volumetric flow rate with the pressure gradient. This is an aperture. The aperture can vary between fractures or even within a fracture plane. And so we have also here, so this is a plot of the pressure, but one has in principle velocities in different fractures that can span various orders of magnitude.
Marco,
yeah.
The aperture you note here is what we call the hydraulic aperture.
Yes.
But it's not the real one.
Well, yes, exactly. Well, it can be.
If the real one can be 10 times larger.
Yes. Yeah. Yes. Yes. But if you have, let's say, a single fracture, a channel, then this would be the transmissivity, let's say. No? It's called the cubic law. If you come across this one. Okay. This was very fast. So now we look at how does transport look like. So one can, let's say, release particles or release a solute in these flow fields, and then what one obtains is distributions of a solute that look like that. No, so they are not. So you have different concentration values. You have high, you have low values. You have a mixing front that becomes relatively heterogeneous. And the same we observe on the Darcy scale. So these are, of course, phenomena that we observe at all scales. No? But here we are talking about, I don't know, millimeter or centimeter, and here this would be a scale of 100 meters or kilometers. And what we want to determine, or what you want to determine often, the observables of interest are, you want to know what is the center of mass position, you want to know where is a contaminant bloom. No? And then maybe you want to know what is the width of this bloom. No? Because on the fringes you have low concentration, in the center you would have higher concentration. And so if you think about cleanup, for example, you need to know where do you start your action. Or you want to know residence time distributions or breakthrough curves. Now residence time distributions, you would like to know if you have maybe chemical reactions, you want to know if the reaction happens, for how long will it happen. Or if you have somewhere a well where you extract fresh water and you have upstream a gas station, they often leak. So they would like to know how long does it take until this contamination arrives here. Now, when do I have to stop pumping, or when do I have from when on can I not use the water anymore because it's contaminated, and when is it safe to use it again? No? So these are some typical observables of interest. And so now the width of a contaminant bloom I can describe using the concept of dispersion. No? The dispersion coefficient describes how fast does a bloom spread. So and here there was an experiment conducted in the 80s in Cape Cod, where solute was injected more or less point-like, and then these colleagues they could image the bloom. No? They had observation wells and they monitored the concentration. And what they saw is that the bloom looks actually relatively concentric, elliptic. No? So there is an increase of the width in longitudinal direction and less in the transverse direction. I said, okay, this bloom I can easily characterize with a center of mass or center of mass velocity and the longitudinal and transverse width. And then Lynn Gelhar, the beginning of the 90s, and his co-workers, they started to compile dispersion values that they observed in different experiments on different scales, going from laboratory experiments to field scale experiments. And what they saw is that this dispersion value that one obtains actually depends on the scale. No? So there is a scale effect. No? The larger the observation scale, the larger the dispersivity. Yeah? So here we are talking about a typical width of what, 20-30 meters. No? So this is something that one cannot achieve with molecular diffusion, which is 10 to the minus 9 meters squared per second. No? Okay. So how can one quantify this transport? So what we use is the advection-dispersion equation in order to describe the evolution of the concentration of a solute. Now, C of x and t is the value of a concentration at a certain position in your medium. And then transport works through advection. So this is the flow field given by Stokes' equation or by Darcy equation. And then we have the dispersion. Tensor dispersion coefficient here. Now this is one way of looking at transport, is a Eulerian way of looking at it through the advection-dispersion equation, and an equivalent way is the Langemann equation, which describes the equation of motion of a hypothetical solute particle. So there is a particle, and the position of the particle that starts at a location A changes due to advection in this velocity field, and the velocity, of course, is given by the flow velocity at the position of the particle. And then one has this random velocity. This object psi of t is a stochastic process. I'm going to talk a little bit about this in the following. And this is the dispersion coefficient. Concentration distribution is simply, say, the ensemble of all particles. No? So this is a Dirac delta here. This is essentially a counting device. No? When you release particles everywhere in your domain, you can say, okay, now I'm going to do a histogram of how many particles do I have in a certain volume. I just count them. and the number of particles is proportional to the concentration. So this is the idea of this maybe a little bit scary looking object, but this angular brackets is simply an average. And this Dirac-Delta is a counting device. So now upscaling, I already motivated it. It's on the one hand a computational requirement, a very serious one, but it's also, let's say, and the more interesting is to gain physical understanding of a system that has many degrees of freedom. Yeah? Okay, so what I'm going to do in the following, I'm trying to give some more meaning to these two equations first, in the context of the dispersion principle. Call it like this. Upscaling from, this dispersion principle is used classically to do upscaling from the pore to the regional scale, and what I want to do now is I want to explain the principles that are behind this philosophy. And I do this in this Lagrangian framework. We consider the equation of motion of a solute particle, dx dt. So we have here a velocity field, which I separate into a mean value and a fluctuation. So fluctuation, first concept. Now because we have a heterogeneous medium, let's say this is a particle trajectory, so this particle trajectory is not straight. No? Because I have heterogeneity, so flow velocities change in space, so this is why the trajectory is tortuous. And when I look at the velocity of a particle, either in a heterogeneous flow field or in Brownian motion, then this velocity is an object that is fluctuating a lot. Yeah? On a given scale. No? So there's actually, we could identify here a scale, I think this was 0.1 seconds. Yeah? But it looks quite random. No? So what one does is, one says, okay, it looks random, very complicated, but it has, let's say, a regular random structure, no? Because I can identify a scale, and I represent this by a stochastic process. Now, a stochastic process is simply a series, in this case, of velocities, no? And each velocity I choose from a statistical distribution. Yeah? That's a stochastic process. And so what we typically require of this stochastic process is that it's ergodic. So what does ergodic mean? Ergodic means that if I have many particles, now typically you have particles in the order of, 100,000, 1 million, or when we talk about diffusion, 10 to the 23 particles, then I would like that each particle sees the same type of statistics. No? Not only this, I require that the statistics that I sample along a trajectory of one particle is representative of the statistics that all particles see. Now this is called ergodicity. Yeah? Because if each particle has its own statistics, I cannot do much in a systematic way. Yeah? This is ergodicity. And stationarity means that the mean value is constant and the variance, what you see here, or the covariance only depends on t minus t prime. So this is a stationary and ergodic stochastic process. This is what we require in this dispersion framework. Okay, so dispersion coefficients. So now we go to the next slide. Exactly, that's the calculation, which we are not going to do at the board. So I want to calculate in this framework the width of the particle plume. No? So I can, by simple integration of this differential equation, obtain the trajectory. It's x of t is the mean velocity times time plus the integral of these fluctuations. Then I can do an average. The average center of mass position is mean velocity times time, and the width is I take x of t, I subtract the mean position, square it, and average it. Yeah? Okay? So if I insert this right-hand side into here, I simply obtain this equation. Yeah? It's a double integral over time, and what I have inside is the covariance function. Yeah? It's really simply you take this, insert it here, put the angular brackets around, and you obtain this formula. It's relatively simple, but it has a lot of meaning because it relates now the width with the fluctuations of velocity, with the covariance function of velocity. And now what I said is interesting for the dynamics is, on the one hand, the center of mass position, the center of mass velocity, which is the derivative of the position, which is simply mean velocity, and the rate by which the width, or in this case square width, increases is by convention 1/2 time derivative of the variance. And so we have derived the Taylor-Kubo formula, which says the dispersion coefficient is equal to the integral of the velocity covariance. But now, even without going through much calculations, we can already say a lot of things. So I mentioned before, the stochastic process fluctuates on a certain characteristic timescale, tau c. And of course, the covariance function is proportional to the velocity variance. So I can write this integral just by some physical reasoning as a velocity variance times the correlation time. So that's the right units, because this is velocity squared and this is time. And all of this, so let's remember this for further on. Your
bracket notation, you say it's an average. How do you define your average here?
Average is an average over all particles. So this is the idea. This is an equation of motion of one particles. So I release many, and then I average over all the particles. At a given time, I want to. Let's go back. So you see this is in principle a distribution of particles. So we put here. This is a random walk particle simulation. We put 10 million particles. We do the histogram. We get a distribution, and we do averages over all particles. And this is why we need this ergodicity principle, because we substitute time averages and ensemble averages. Please ask questions. If I'm too fast, or you can interrupt me, no problem. I will remember you.
Quick question on that integral. Are there any assumptions about the well-behavedness of the distribution? So that sometimes those integrals, if it's a Pareto distribution or something like that, it might not integrate.
Exactly. Yes. Very good. Yeah. So here we assume, of course, that the variance exists. The velocity variance exists.
It exists. Okay.
Yes. Yes. Yeah. But this is something that in a porous medium you always have. Let's say that the velocity has is not the velocity distribution does not have a mean or variance. It's very, very unlikely in porous medium, because you always have a cutoff. There is always the largest velocity. And the medium, so we have laminar flow, so the medium is giving resistance, so you cannot, and you have a pressure gradient as well, so you cannot get to, let's say, this type of Pareto type distributions. This is more when we talk about residence times or transition times. We will get to this a little bit later. Okay. So good. So assumptions, we have to recall this for later, is we need a finite correlation time, tau c, which we typically assume is very small compared to our observation scale. This is when these averages become meaningful. And we do a stochastic model for the velocity, which is ergodic and stationary. Okay. So now, let's say with this simple principle, I will put it here, this dispersion coefficient is equal to velocity variance times correlation time. We can already do the upscaling. So molecular diffusion. So first example, I put molecular diffusion, because it's an upscaling to go from molecular dynamics to let's say a mesoscale or a macroscale description. Molecular diffusion, the correlation or the characteristic timescale is the mass of the particle divided by 6 pi eta. This is a dynamic viscosity times the radius. So this is a Stokes drag. Let's go to the next slide with the calculations. Because in order to obtain these timescales and variances, one has to look a little bit into the process that creates this motion. And for diffusion, it is the Newton's second law, which simply says that mass times acceleration is equal to force. So here I have already divided by the mass. So the force on the right side is, I have a random force, because small molecules, they collide with larger molecules. There's a random motion. This is the randomness that we have in diffusion. And then we have a drag force. That is because the particle is going through fluid. This is how viscosity comes into play. And then this drag force is giving a time scale. tau c, a characteristic timescale, and the drag coefficient is simply what I just described. And then we need an expression for the velocity variance now, so we need to find out what is the correlation length, or what is the characteristic timescale, and what is the variance. So the timescale we have obtained from drag, and the velocity variance we get from an energy consideration, because the kinetic energy of an ensemble of particles is simply given by the equipartition law, is the Boltzmann constant times temperature divided by 2 for each degree of freedom. You get this 1/2. And from this we immediately obtain the variance. It's Kb times temperature divided by mass. No? And with this, simple reasoning, we end up with the Einstein-Smoluchowski formula. No? The diffusion coefficient depends on temperature and on the size of your particle, but it's independent of the mass. Then we have dispersion in the tube, Taylor dispersion. This is a phenomenon that is also driven by hydrodynamics and by diffusion. So you may be familiar with this. We have a tube, we have a laminar flow, you get a parabolic velocity profile, you have zero velocity at the wall because of no slip, and then towards the center you get increasing velocity. Velocity profile is parabolic. And so now what happens? Particle that you release here is going to sample by a random walk, by diffusion, to the flow velocity. Each flow velocity is constant. Now at each height or each radius, the flow velocity is constant. So the velocity field that we have here is non-ergodic, because a particle that moves on a streamline without any diffusion is not going to see any other velocity. It sees always the same velocity. No? So each particle sees a different velocity, so there's no ergodicity for the flow. But by diffusion it can sample the velocities. And now we can think about what are the characteristic timescales in this problem. One is the diffusion time over the channel or the pipe cross-section. No? So you have here a finite set of velocity values from which the particle samples its velocities. No? So when you are very close to your initial point, you are very correlated still, no? Because you can even go back to the same velocity, you have a strong correlation. But once you mix over the cross-section, you basically, every particle sees the same statistics. No? Then we have a kind of an ergodic situation. So the characteristic timescale for this is the diffusion scale over the cross-section. The velocity variance in this example, velocity variance is actually always proportional to the mean velocity squared, because you have a higher velocity, you get a higher variability. And so here the velocity we can also relate to momentum conservation, which what we did with diffusion. So here is simply from the Stokes equation we directly get mean velocity is equal to the radius squared times the pressure gradient divided by A times dynamic viscosity. And now we use this formula, which I should not have erased, which is sigma v squared times tau c. And we can assemble the Taylor dispersion coefficient. It's mean velocity squared, aperture or diameter squared divided by molecular diffusion. Yeah? So this is correct up to a constant. No? Yeah? This is actually a proportionality sign. No? Okay, next is Okay, next is hydrodynamic dispersion. So now we have talked about diffusion, we have talked about Taylor dispersion, and now we look at dispersion in a porous medium.
Marco,
yeah.
Before you go off of diffusion, what I've been reading through the literature, they define diffusion in 6 different ways, from diffusivity to multiple ways of defining effective diffusion.
Yes.
And is there a way to differentiate between them? What should you be using for?
Okay, so look, diffusion is what I described on the previous slide. Now, so this is diffusion. Sorry. Okay, I should do it on the computer. It's too confusing. This is diffusion in a free fluid, no? or in a gas. Now, if you have diffusion in a porous medium, then we call about effective diffusion coefficient, which is basically the molecular diffusion coefficient multiplied with the tortuosity multiplied with porosity. No? Then Taylor dispersion is, it's not diffusion, this is why I call it dispersion. And this Taylor dispersion is caused by velocity variability. No? It's a type of hydrodynamic dispersion, no? Because it is driven by hydrodynamics through this term here. And then the same when we go, let's say, same terminology when we go to porous media. So here actually I use the term hydrodynamic dispersion because the other one is Taylor dispersion, that's the name of it. No? So here we talk about hydrodynamic dispersion is if we have a porous medium, no? Let's say we have some grains, what you saw before on the slide. And then this would be a streamline. And now we can think about what is the correlation, what is the typical correlation time here. It would be a pore length divided by the mean velocity. Yeah? This would be a characteristic time scale because the streamlines are bended, so this means the velocity varies along a streamline, and over to a characteristic length scale, you can say the velocities change. No? Exactly. Again, the velocity variance is proportional to mean velocity squared, and now we can assemble our hydrodynamic dispersion coefficient. It's simply variance times correlation time. It's the mean velocity times the pore length. This gives you a rule of thumb. If you say, if I know the grain size or the pore size, I can estimate hydrodynamic dispersion, or it's also sometimes geometric dispersion. Now you ask something else about dispersivity, for example. No? Dispersion, dispersivity, effective diffusion, effective dispersivity. There is actually a paper that is called Diffusion, Dispersion, Confusion. This, by Fred Molls, I think. If you want, I can send it to you. But, so dispersivity, often called alpha, is the dispersion coefficient divided by the mean velocity. That's a length scale. Yeah? So here, for hydrodynamic dispersion, the dispersivity is simply the pore length, or the characteristic pore size. Yeah? See? D divided by V is here simply LP. No? So this gives you a rule of thumb. Now, if you have some idea about the material, the porous material, you can make an estimate. And again, the hydrodynamics comes from the mean velocity, which is permeability. The mean velocity is permeability times mean pressure gradient, or pressure gradient divided by dynamic viscosity. And now we go to macro dispersion. So this is now a different scale. Now we go to the tens of meter, hundreds of meter scales, but the principle is always the same. We have a characteristic length scale, LC. So this length scale is now the correlation scale of your medium. No? I said we are representing heterogeneous medium in a stochastic way, no? With this multi-log normal distribution of hydraulic conductivity, where I said you have a map and you assign a random conductivity value to each, let's say, voxel or pixel, and but you do this in a correlated manner. No? So the correlation length is LC. Then we have a mean velocity. This gives, again, with the same reasoning as here, the characteristic correlation time. Variance, again, is equal to mean velocity squared times the variance of your log hydraulic conductivity. And now we can assemble the macro dispersion coefficient. It is the variance of log k times mean velocity times no, this should be LC, sorry. This is the correlation length of your hydraulic conductivity field. And then the hydrodynamics comes through the Darcy equation. Now the mean velocity is now effective conductivity, another upscaling parameter, but we are talking about flow, about transport, not about flow. No? So this is the upscaling, the equivalent dispersion coefficient, but for flow, it's the effective conductivity. That's a different lecture. Maybe Philippe is going to say something about it. Okay, now with all of this together, we have determined the dispersion coefficient. We have parameterized it by hydrodynamics. and by some understanding of the system, and now we can write down a Langemann equation and an advection-dispersion equation. We can identify the characteristic scales, which we have discussed. There is in principle two characteristic scales in the system. It's the advection scale and it's a diffusion scale. And the Peclet number, a very important non-dimensional number, compares these two timescales and tells us something about the strength of advection and diffusion / dispersion on the length scale of interest, and the length scale where we are interested on. This is very important. So it's not a number that you can use without thinking. Now you have to think on which length scale you want to compare processes. Because on a very small scale, Peclet number is small. Small Peclet number means dispersion dominates. On a large length scale, Peclet number is large, advection dominates. No? So you have to think about what is the characteristic length scale in your system. So now I want to maybe just sketch how one can obtain these two equations from what we discussed before. No? So what we had said before is that we have velocity fluctuations that are correlated on a scale tau c. No? Okay, now in order to derive these two equations on the previous slide, we want to think now on the microscale and how we can obtain this from very simple principles. So velocity fluctuations, we said they are correlated on a given finite scale. So the simple thing to assume is they are exponentially correlated. No? So if the difference of these two times, t minus t prime, is very large compared to the correlation time, the correlation decreases exponentially. No? So this would be t minus t prime, and the correlation function looks like this. Now I have two exponential tails, and the characteristic time scale is this. Yeah? So now what I do is, I mentioned this before, we say our observation time is much, much, much larger than this correlation time scale. No? So what I do is, I say, okay, I multiply this exponential by the correlation scale, and I divide by the correlation scale. Yeah? So I separate the scales out. So now this object, this is a Gaussian distribution, no? An exponential distribution. So I said the correlation function itself is exponential, but now I have split it in a way that I have an exponential distribution and multiplied by a time scale. So now if I let now the time go to 0 in this object here, what does it mean? This means this exponential becomes higher and higher and narrower. Yeah? And this is the property of a Dirac delta function. Now Dirac delta is putting an infinite weight at a time t equals 0 in this case. Yeah? So I'm representing the correlation function as this singular object, which makes calculations very easy. Yeah? And then I look and I say, oh wow, here I have the diffusion or dispersion coefficient times 2 times this Dirac delta function. Perfect. Okay, now I have a delta correlated velocity, which essentially says velocity is uncorrelated. Yeah? Because on times that are very large compared to the correlation time, I have 0 correlation. This is what I want. And then I represent the velocity through its strength and then an object, psi of t, and this is an object that is wildly fluctuating and which is fully uncorrelated. No? So at each time you choose a random value from a statistical distribution. This can be any distribution that has a finite mean and a finite variance. And as we will see in a moment, thanks to what is called the central limit theorem, the specific distribution of this object doesn't matter. But when you sum it up, you will always end up with a Gaussian. So this is the idea. Okay, so now we can represent the motion of a particle as the xt, mean velocity, plus this random velocity. And now we discretize this equation. In fact, so this is stochastic differential equation. This is the mother of all stochastic differential equations. It has only really a meaning when one discretizes it. So we do a discretization in delta t in time. So Tn is n times delta t. Then I have particle position after n time steps. N plus 1 is xn plus this displacement by mean velocity plus this random object, which is the integral of this noise psi of t. No? So now what we need is it's all about statistics. We need to have a statistical characterization of this object, and the mean value is of course 0, no? Because psi has mean 0, and then we look at the variance. So the variance of this we can calculate, no? Because we have the explicit expression. So here we have the correlation function. The correlation function is a Dirac delta. So if I integrate this, the integral over Dirac delta is 1. Yeah? So what we obtain is we just get 2 times d times capital delta t. Yeah? So this increment squared is proportional to delta t. So this means the increment itself is proportional to the square root of delta t. Yeah? So this is a remarkable property which is at the heart of any stochastic calculus. Yeah? And so now we can consider space increments. So what is the distance that the particle moves at one step? Delta xn. The increment is of course mean velocity delta t times the stochastic increment, which we have just which we can characterize. Mean displacement v delta t, mean displacement squared v squared delta t squared plus 2d delta t. Position of and what we are interested in is the position of a particle at a certain time. We want to do this for all particles. Then we want to do a histogram of all the particles at different positions, and this gives us a concentration. No? So now what we have here is position of a single particle is the sum of random increments. Now I call this now zeta. So these objects have mean 0, variance 1. So now if I have a sum of independent random variables, central limit theorem tells us if mean is finite, variance is finite, the distribution of the sum is a Gaussian. It's Gaussian distributed, yeah? It's very fundamental. And now we want to determine what is the distribution. So the concentration of particles after n plus 1 steps at a position x, this is a simple conservation law, is the distribution of the particles after n steps at a position minus x prime, x minus x prime, times the probability that your particle is jumping to the next position. Yeah, very mass conservation. Yeah? I think should be relatively intuitive. Now, and from this now we can construct this advection-dispersion equation, because what happens is, so we said this increment, so p delta is the distribution of our delta x, now, which we characterized by the mean and the variance. Yeah? So now we can construct from this the advection-dispersion equation by noticing that x prime is going to be very small. Now we see the increments, they scale with delta t. And of course, eventually we would like to get delta t to 0, no? Because we want to have a mathematical description that is continuous in time. No? So we have to take the continuum limit, delta t very small, and then of course these increments, they're going to be extremely small. So what do we do if we have a function that depends on something plus a very small thing? We do a Taylor expansion. Yeah? Are you familiar with Taylor expansions? Some of you. Okay, let's have a look. So what we do is do Taylor expansion. So the first zeros out of the Taylor expansion is the function itself at the value x. No? So the next order is I have to take the derivative of this function and I multiply it with the small quantity x prime. No? And then there should be a plus sign here. I'm sorry, this escaped me. We have a minus sign. Here we have a plus sign. And then we have the small quantity squared divided by 2 times, and this should be the second order derivative of concentration. Yeah, I will correct this in the version that you can download. Okay, so that's it. We have done a simple Taylor expansion, makes complete sense, and we have neglected all the higher order terms. Yeah?
So, quick question. Integrating over all space, but we've said that we know D is spatially is scale dependent.
Yeah, no, but this, look, okay, very good. So the scale dependence we have already taken care of. So maybe I should have I should have said this more explicitly. So this is how we take care of the scale dependence. Now we said hydrodynamic dispersion. We have found out it depends on something that is dependent on the hydrodynamics and something that depends on the geometry. So this is the length scale, this is scale dependence. It depends on the characteristic scale on the scale you're operating. So here it's the pore scale, and here it's the correlation scale of hydraulic conductivity. So here the correlation scale is on the order of tens of micrometers, or hundreds of micrometers, and here the correlation scale is in the order of meters. So now here you have the scale dependence explained. Yeah? So this is scale dependence. And not only this, it's not only that the scale dependence is explained, also in this whole, let's say, framework of thinking, we have derived this Langemann equation, and we have derived the advection-dispersion equation, and we have found is that mean and variance are totally sufficient to characterize transport. Yeah? So now I know what you're aiming at, John. You're aiming at that D can be a function of space, for example. No? But this is then, when we get to this again. Wait, okay, let's go back here. Oof. Too far back. Wait.
Yeah.
This one, exactly. So now what we have done now was an upscaling exercise, for example, from the pore scale to continuum scale. So then the continuum scale, if we are on a centimeter scale, my velocity would be constant and the dispersion coefficient is constant. Now I go to a larger scale, meter scale. So now I have heterogeneity or to tens of meter scales, I have different materials. So my flow velocity varies in space, and so does hydrodynamic dispersion, because it depends on the flow velocity. So this is how you get a spatial dependence here. No? Yeah? But then we have heterogeneities on a different scale, and we can treat these heterogeneities in the same way, within this framework, in the same way. We identify a characteristic length scale, we identify the mechanism of fluctuation, and we can now derive this advection-dispersion equation for the next higher scale. No? So this is the idea in this doing upscaling using dispersion. Okay, but now let's say we go from the pore to the continuum scale, or we go from Darcy scale to a regional scale, and in the regional scale we can consider as homogeneous, because we assume that it's much larger than the typical correlation scale of conductivity. The same as on the Darcy scale, we assume is much larger than the pore scale. And then we have this simple description in terms of advection-diffusion, advection-dispersion equation, and Langemann equation. So and these are transport characteristics. I think Tomasz looked at some solutions of the advection-dispersion equation. I just repeat this. So if you inject here at 0, for example, a solute instantaneously at a point, and you let it evolve according to these two equations, you obtain as the spatial distribution a Gaussian. No? Very fundamental, you should all remember this formula. And what it says is that the center of mass moves with the velocity v, and it spreads out with the velocity d. No? So this tells us where the plume is and how wide it is. So this is the first two observables, mean velocity, spatial distribution. The last observable is the breakthrough curve. I would like to know, I'm sitting at a point where my well is, and I want to know what is the time series of concentration values that you can observe. And this is described by something that looks like a Gaussian, but it's called an inverse Gaussian. Now, this is a distribution in time. This is a distribution in space. Now, so if you integrate this over x, it's going to integrate to 1, the way we define it. And this object here is integrating to 1 if I integrate over time. No? So the area under these curves is 1. Yeah? And these are the characteristics of Fickian transport. Now we want to look at another characteristic, which is going to be very interesting when we look at non-Fickian transport, which is residence and trapping times. And here we look at residence and trapping times for purely diffusive transport. So now imagine, for example, in a fractured medium, you have your fractured channel and you have a porous matrix, and then solutes can diffuse from the fractured channel into the porous matrix. No? So in the matrix, you will have predominantly diffusion as transport process because the velocities are very low. So now we can ask, if I have solute in an immobile region, how long does it take for the solute to diffuse completely out? No? And what we see is that the residence time distributions, they have what we call a tail that goes like t to the minus 1/2. And then for the time, let's say the characteristic diffusion time, tau d, it goes to 0. No? So it's like, imagine, now we have, this is L, this is X, and initially we have diffusion C, for example, equal to 1 over L in our medium. So the total mass in the system is equal to 1. No? So now I open this boundary here and I let solute or particles move out. So what I get is I get a very high flux at small times, and then let's say the mass inside the medium is a measure for the distribution of residence times. No? The more, let's say, the mass that is left has the largest residence time. It decreases like t to the minus 1/2. It's a power law. It's actually heavy tail distribution. But then we get an exponential cutoff because at a certain time everything will be out. No? If we open, if we let this boundary go to infinity, this distribution is actually not defined, no? Because it's not normalizable. So now when another object that we can consider is the trapping time distribution. So a trapping time distribution is that, we say that here is a fracture. So now what happens is a solute particle or solute decides to go inside the matrix, then it diffuses around a little bit and it goes out. No, it's trapped for a certain time and then it leaves. And this trapping time distribution has also a heavy tail. It goes like t to the minus 3/2. It's simply, in a certain sense, the derivative of the residence time distribution. Yeah? And to motivate these two things a little bit, we can do some small calculation. And the only thing that you need for this calculation is to realize that if you have a diffusion front, this diffusion front grows like square root of time. Yeah? So we have seen this a few times. Square root of time is, say, when we talk about diffusion, there is often a square root involved. So diffusion front, now if you have an initial condition like this, I think Tomas presented the solution. You have a step initial condition, and then you start diffusion. What happens is your diffusion front is going to increase, no? And the width of the diffusion front goes like square root of time. Yeah? That's a signature of diffusion. So now simply with that, and the diffusion equation, yeah, for this residence time setup, what we say is that, so this is the matrix, this is the boundary that we open, and what we have at this boundary is we have a concentration of 1 for times smaller than 0, and at time equal to 0, we let the diffusion go to 0 at this boundary. Now we are opening the boundary and let stuff diffuse out. This is our initial distribution. Is concentration is simply 1 over L because I want to have it normalized to 1. And on the right side we have a no flux boundary. No? The derivative of concentration is 0. So then we realize that the probability that the residence time is larger than a given time t is simply equal to the mass that is left in the system, which is equal to the integral of concentration. And then my residence time, PDF, is simply minus the derivative of the mass that is in the system. Huh? So and then we can write down an equation for the mass. simply by integrating the diffusion equation over the whole domain. So I get dm dt. What you have to do is you have to use the you have to integrate this flux. So this is a double derivative. There is a square missing. It's a double derivative. Integrate by 1, you get a single derivative at the boundary. So this is the flux over this boundary. But this flux is concentration times diffusion divided. No, but this is a derivative. A derivative is delta C divided by delta X. And this delta X is the scale over which the concentration varies. And this is clear, there is only one scale over which it can vary, is the scale of the width of the diffusion front, S of t. And with this, we get dm dt, 1 over square root of t. The PDF is equal to the derivative, which we have just calculated. So now we have, with very simple means, determined the scaling of the residence time distribution. Yeah? So you see there is no big math involved, it's only reasoning. Yeah? It's all elementary calculus. The next thing is the trapping time distribution. So now we have determined the residence time, and the trapping time we get for free. Now, because we said the trapping time is essentially a particle goes in, diffuses, goes out. But what does this mean mathematically? I'm putting a Dirac delta pulse on the boundary. No? I'm injecting instantaneously at time equal to 0 a particle. This would be a Dirac delta pulse here. Otherwise, I have no solute initially inside the medium, and I have a no flux boundary, the same as before. And the same as before, the probability that the trapping time is larger than a certain time t is equal to the mass left, and the PDF then is the derivative of the cumulative probability. And now I realize this problem is very strongly related to the previous one, because I can simply derive let's say the concentration that I have for my residence time problem, and I obtain the trapping time problem. Yeah? So I get the trapping time for free. Yeah? And this is how we see that the trapping time goes like t to the minus 3/2. So what we have determined is the power laws, which are something that we are typically very interested in, is these behaviors. And then just by physical reasoning, it's clear that these power laws, they have to be cut off on the time scale that is needed to empty the whole medium. No? And these time scales, they can be quite big, no? Because we have in a porous matrix only diffusion as a mechanism, and it's actually effective diffusion. It's molecular diffusion times tortuosity times porosity to some power. It's very slow, and this is how we get to the summary. No, because we said diffusion is very slow. But what we assume in this Fickian, in this dispersion principle, is that we have characteristic timescales, tau c, on which our process happens, and we always assume that this characteristic timescale is very small compared to our observation time. Yeah? And if this is the case, we can write down very simple stochastic processes in which increments are independent from everything that we had before. This is called a Markov process. You have a minimum memory. No? So you don't have to remind everything. At each step, you are sampling a value from a distribution. You don't care about what happened before. And this is fantastic. So this whole principle, because it's valid across all scales. Now we have used the same principle on the pore scale, on the continuum scale, on the regional scale, any scale. Because the way that the transport works is the same. No? And we have parametrized it. No? It's not only that we have used, let's say we have derived an equation for it, we also have derived a way to parameterize the equation by medium properties and by the hydraulic or hydrodynamic properties of the process itself. So now I already hinted at that this correlation time that we assume to be very small compared to our observation time, this is often not possible. is not valid. No? Because in this matrix diffusion example, you saw this, matrix diffusion can be weeks or years. No? This is maybe timescales that are relevant for nuclear waste repositories, but not if we are interested in making predictions over half a year or a year. Okay, so now beyond dispersion, some examples. So we saw, I presented this Cape Cod experiment before, which was very nicely showing how the dispersion principle can be applied to predict contaminant or tracer transport. And then a few years later, or maybe around the same time, people designed another experiment in Columbus, Ohio, I think, and it was called a MADE experiment. MADE means macro dispersion experiment. And the idea was to have another experiment that is confirming the theory of macro dispersion. No? But in this case, it was not working. No? So here, essentially, there was also a relatively point-like instantaneous injection of tracer, and then there was a series of monitoring wells to monitor the concentration at different heights, at different positions. And so I said this was an instantaneous injection. So what we would expect would be a tracer plume whose center of mass moves downstream. So what was observed was that, wow, this looks more like a steady state plume. Yeah. After 49 days, 279 days, 500 days, almost 2 years. Yeah. And what one got was this elongated object. Actually, when you look at the integrated profiles, there is a peak of concentration here and then a long forward tail. So what does it mean? So it means something is not working with our assumptions. And what happens in this case, what happened here was that the injection was not a point injection, it was an injection over volume of an area. And already in this volume, you had heterogeneity. You had low conductivity and high conductivity. And then in the low conductivity, you have low velocity, so you're retaining the solute. No? So this is one of the interpretations of this observation. So okay, macro dispersion, unfortunately not working. Then this is an experiment that was done in the group of Charlie Harvey, who was also here this week, by a former student, Brandon Zinn. And they wanted to test transport in media with high contrast. So this is a coarse sand in the back and fine sand with low permeability in these inclusions. And so initially everything was at a given concentration. Then it was flushed by clean water. And what you see is that this is the residence time concept. So solute is retained and it's slowly diffusing out. No? So here we have a time scale in the background medium, which is relatively small because the flow velocities are high. But then we have another time scale, which is the one for diffusion out of these inclusions, which is very long. Now we have a disparity of time scales. Yeah? So this is not in the spirit of the dispersion principle. And other example, so this is an experiment that was conducted in Plumeur. I think this was done by Peter Kang, Tanguy Le Borgne, and the team from Rennes. And so what they did is, so this is a fractured medium, and they did a push-pull test. So they injected water with a certain solute concentration, pushed it out, and after a certain time they pulled it in. And what they did is they measured the concentration at the injection withdrawal well. And what one would expect from this Fickian theory would be in log-log scale asymmetric distribution with exponentially decaying tails. And what was actually observed, and not only in this experiment, in many experiments that were conducted in fractured rock, is a long tail. And of course here the phenomenon can be diffusion into the matrix, because you get a slow diffusion out. But the diffusion in the matrix has a signature of exponent 1.5. Remember, this was the trapping time. It's a 1.5, because we're pushing in, solute gets trapped, released, and here they observed 1.75. So there is another mechanism, but can be this we get to later, can be slow advection as well, no? Because we have very narrow fractures, we have wide fractures. And then we have another experiment on the lab scale. This was conducted at ETH in Zurich, and here the colleagues, they focused on the properties of the velocity process. No? What they looked at is at velocity increments. No? The velocity increments, if we choose them, the velocity increment would be delta v is v of t plus delta t minus v of t. Now it's an increment, and if I choose delta t large enough, the two increments should be independent. No? This was our stochastic process. I choose delta t much, much larger than the correlation time. These two increments should be independent. If they're independent and Gaussian distributed, another thing that goes along with the dispersion principle, then we should obtain the distribution. Let's say a convolution of two Gaussians is a Gaussian distribution. So we should actually observe a Gaussian distribution for the increments, and what is observed are these type of distributions. So there are typically peaks at zero. A peak at zero means delta v equal to zero, means that this difference is zero. So what it means is that the velocity at a time t plus delta t is more or less the same as the velocity at a time t. So this means we have strong correlations. No? So this showed that this, again, this assumption that there is a very clearly defined correlation time is not valid.
What are ABC?
Huh?
On the plot you have ABC.
Different experiments.
That plot you have.
Different experiments.
Oh, okay.
Experiment A, B, C. Sorry, I should have said it. Yeah. Okay, so now a summary. Fickian transport. Assumption was particle velocities decorrelate, timescale tau c. We have a temporal Markov process. This is a Fickian assumption. What we observe in many experiments is that actually transport times are broadly distributed, and particle velocities do not describe this Markov process. We observe intermittency. Now when you observe intermittency, this means there is correlation. Okay, so now the question that we have is there another principle that is there maybe another principle that we can use similar to this dispersion principle? And so now I want to talk about the mechanisms of non-Fickian dispersion. So first we need to understand the processes, the dynamics, the mechanisms, and then we can come up with a new theory. So there is one example, I just want to go through this quickly, which is called, as one call it, the Matterhorn-de-Marcilly model, where they were thinking about this dispersion principle maybe does not work. No? So let's ask the question, is transport in porous media always diffusive? And they come up with a counterexample that is actually relevant, because in many porous media one sees these stratified geometries. So this would be a medium in which you have different hydraulic conductivities in different layers. You have the Darcy equation. Simplifies a lot, because what you simply see is that the flow velocity is equal to the hydraulic conductivity in the layer times the pressure gradient, the height gradient that you put. There's a minus sign missing here. And then the transport we consider in this Lagrangian framework. We have a mean velocity and the velocity fluctuation. No? Velocity fluctuates across strata. And in transverse direction we have only diffusion. No? So and then with a relatively elementary, so you can do a very complex calculation or you can do a simple calculation, and you come up with the same result, that actually the dispersion coefficient is not going to be constant. It's going to increase like the square root of time. No? So what happens is you put particles here, each particle moves with its own velocity. So at very small times, the distance between particles is increasing linearly with time. Now, this means the square distance is increasing with the square of time. No? Let's say sigma squared at very small times goes like t squared. No? This means the dispersion coefficient, which is the derivative of that, is linear. This is called ballistic dispersion. And then eventually, at a certain time, which is related to the strata width and the mean velocity, is going to become, let's say this is a double log plot, goes like t to the 1/2. Okay, and what we expect from the dispersion principle is that it becomes constant. No? So what happens if your medium is finite? So that you have here an impermeable boundary on top and on the bottom, and it has the width L, then it cannot increase. Let's say dispersion coefficient cannot increase infinitely. Then we have a similar situation as for Taylor dispersion, because solute is going to be mixed over the cross section, and it freely samples at a certain point from the velocities that you have in the strata, and then we obtain a finite dispersion coefficient where this time t is simply substituted by the cutoff time, tau d, no? And then actually we have a similar behavior as for Taylor dispersion. So the simple way of deriving this is in 2 lines. So you say v of t is the velocity of the diffusing particle at the position of the particle in the transverse direction. So now we can think, okay, we need a correlation function, no? Because we want to use this Kubo formula. Yeah? We will put it again. So d was equal to integral from 0 to t dt prime and the velocity correlation function. So the velocity correlation is particles can diffuse. Oops. Particles diffuse and they can come back to the same stratum. Now I can ask, what is the distribution of return times? Distribution of return time, probability to return to a certain stratum we have already calculated, is related to the trapping time distribution, which goes like 1 over t to the minus 3/2, and the probability is the integral of that, so it goes like 1 over square root of t. No? So this is the correlation function of velocities, goes like 1 over square root of t, and then the dispersion coefficient is the integral of that, goes like square root of t. Yeah? So this is a simple way of obtaining this result with elementary calculus. And now another mechanism. So this mechanism was correlation. Another mechanism is trapping. We have already discussed this. These are simply examples, computational example from solute transport in a fractured medium. This is a laboratory experiment that was done in the group of Pietro De Anna. This here was done in the group of Sebastian Geiger. And so you see there is trapping in the matrix. Here we have trapping in dead-end pores. No? So these trapping times, they determine transport. And so how do they determine it? No? So in matrix diffusion, we have determined trapping time goes like t to the minus 3/2. We can assume that trapping events, they occur more or less at a constant frequency. And now I can ask, okay, breakthrough time. Now what is arrival time at a certain distance? So now I say I have distance L. Now, how many trapping events are going to occur? I have a constant rate at which trapping events occur, multiplied by the time that I need to traverse inside the fracture from 0 to L. This gives me the number of trapping events, and then the arrival time is simply the sum of the trapping times, because I assume that the advection time in the fracture is going to be very large. It's very small, no? Because velocity is high. So now my arrival time is simply the sum of these random trapping times. And now there's another central limit theorem, which is called the generalized central limit theorem, which means if you have a heavy-tailed random variable and you sum it, then the sum of that is again a heavy-tailed random variable, which has the same exponent as the variable you are summing. So this means if our trapping time goes like t to the minus 1 minus beta, and this beta is 1/2 for matrix diffusion, then my breakthrough curve is having the same power. So it's a conservation of power laws. Now, power law in, power law out. Now, so this is the signature of matrix diffusion. When you happen to have to do some tracer experiment in fractured rock, it's possible that you obtain t to the minus 1 minus 1/2. Okay.
Marco,
Yeah.
you wrote alpha and beta.
Sorry, yes. See? Sorry. This should also be beta, and this is 2. Yes, I will correct this. Yeah, of course, what I mean. The same power law that you observe for, let's say, the trapping time is the power law that you get for the breakthrough curve. Yeah? I'm using alpha and beta sometimes, and sometimes I mix them up. But it's the same exponent. No? So here we have 1 minus beta, here we have 1 minus beta, and the exponent beta is between 0 and 2. Thank you, Tomasz. So these are mechanisms related to trapping, and then we have also advection. Well, because now we have only talked about diffusion, trapping, no advection. But what we have, as you can see, we have a very broad distribution of velocities. No? And flow velocity, we have said in the very beginning, changes along a trajectory. But it changes on the characteristic length scale actually, because all of these flows, they are stationary and they are imprinted in a medium. No? So I have a narrow conduit here. I can have a very low velocity. I have a wide conduit, I have a high velocity. Or here I have low conductivity, low velocity, high conductivity, high velocity. And if I think now about times, actually the transition time now to the time to transit over a conduct, over a pore conduit, or over a certain area of hydraulic conductivity is related to the characteristic length scale and to the velocity that I have at this point. And if the velocity is very small, this transition time can be very large. So in principle, I can have a very broad distribution of transition times, and the mean is not representative of that. No? Normally I can define a mean advection time, but I can have a sizable amount of particles of solute transfer that is occurring on timescales that are much, much longer. No? And this I can have on different scales. You see, so now we are shifting from a principle of characteristic time to a principle of characteristic scale. No? And so the way to formalize this is to go from what I call a time Lagrangian viewpoint. This is what we discussed with the dispersion principle. We said movements occur at constant time increments, no? Tau c. So they occur at constant frequencies in time. No? But if the velocities do not decorrelate on this time scale tau c, then this is, what I would need to do is I have to say, okay, I have velocities that are correlated on a very long time scale, others on a small time scale. Then I need to make my stochastic model more complicated. No? The stochastic model that we discussed in the dispersion principle was very simple. It was one step, new velocity, other step, new velocity, freely sampled. So now here I have to invent, or I have to represent this correlation function. I have to use a correlated random process, no? More complex. No? But if I change the point of view and I say, but look, velocities that don't change on a characteristic time scale, but on a characteristic length scale, this is what we see in porous media, then I can get again to a very simple stochastic representation. Namely, now the velocities at each step of my new random walk that I do in space, let's say instead of time, at each step I can sample a new velocity which is which I sample independently from the previous ones. But it does not come for free, because now I have my spatial motion and I have to keep track of the time. So because now each transition, each step has a different time, no? Because it's the spatial scale divided by the velocity that you have at that moment. No? So there is a little complexity a little bit more of complexity, because I have now two equations. Or let's say I have now time as a random process, and here we had space as a random process. No? This is what, in principle, let's say the complexity comes from what we are used to think. We are used to think in things are occurring at a constant frequency in time. Now we have to think that things are occurring at a constant frequency in space. No? And this means time is variable. Okay. So if we now take this point of view and we look at velocity series, this is a velocity series that we sampled in on the pore scale sampling at constant frequency. No? So what you see is that when you have a very low velocity, you are there for a very long time. No? Because the residence time in a low velocity is large. And when you go into a high velocity, you are fluctuating a lot now because you change the velocity very quickly. But if we change the point of view and we sample the velocities now at a constant frequency in space, then the velocity signal looks very regular. Let's say it does not look regular, but when you look at it from a stochastic point of view, it's perfectly regular because you can represent this by a very simple process. And the same you observe. So this was pore scale. This was a simulation on let's say, regional scale. Same observation, and this is on a fracture scale, DFN scale now. We have sampling in time, sampling in space. So these are two examples of sampling. So we do a sampling in time of velocities, which means this is our indicator function that helps us to make a histogram. We sample along a trajectory going along in time, and this is a Lagrangian velocity distribution because it's the distribution of a particle. That's the distribution of velocities of particles as they move. And here one can show this is actually the same as when you sample velocities in space. No? So you solve your flow problem, your Darcy equation, Stokes equation, and then you just do a spatial sampling. No? It's a flow property. This is a flow property, and this is a transport property, and they are related in a very simple way. They're equal. But when we do equidistant sampling, so I go along constant delta s's along a trajectory, then we have this prescription, and what you can derive in a simple way by doing a variable substitution here, ds is equal to v delta t. You see that now this velocity distribution for equidistant sampling is related to the distribution with isochrone sampling just by a velocity weighting. What is the idea behind this? No? The idea is that when you sample in time, you are giving much more weight to low velocities, because you are sampling many more. So here, here I would sample at constant delta t, and I'm sampling this low value very often, so I give it a lot of weight. No? But if I do equidistant sampling, I give each velocity the same weight, more or less. No? This is why we have to do this velocity weighting. But these things are very important because now these relations, they tell us how we can parameterize a model. Yeah?
This is true only if the aperture is constant.
Yes, exactly. So this is.
Otherwise, it's not the number of particles you have in one place is related to the flux, which is the velocity multiplied by the.
Exactly. But let's say this. No, very good point. So this is, or when you have variable porosity. But this one is purely kinematic. Right? I mean, the relation between Eulerian PDF and Lagrangian PDF. This is what you need now. So what you need here in order to derive this is you need that the flow is divergence free. And this is what Philip means. So when you look at the transport velocity, which is flow velocity divided by porosity or aperture, then this is not divergence free anymore. But there are ways of dealing with this, but this goes beyond this lecture today.
Next complexity.
Yeah. Yes?
But is it true for the Stokes equation that it's ergodic in that way in all geometries? You can sample a Lagrangian trajectory and get at the Eulerian velocity distribution?
Yes, this is true for any divergence-free flow.
Okay.
Yeah?
But even with inertia?
Yes.
Okay.
So the only thing that you require in order to show, well, what you need, okay. Well, we can discuss it later. No? I mean, there are some subtleties here. But what you need is, so in order to show this relation, you need two things. Velocity conservation, volume conservation, and ergodicity. Yeah? But if you're interested, we can discuss more later. Yes? Yeah?
I didn't really understand the idea that the bottom one doesn't apply for variable aperture. It's still true.
No. No. What does not apply is this one here. This equation.
Because
This always applies. It's purely a kinematic. It's a kinematic relation. So what does not apply is this one here, to go from Eulerian to Lagrangian. It does not apply. No?
Because of lack of methodicity?
No, because the velocity is not necessarily divergence free.
Okay, because of the...
You have variable porosity or variable aperture.
Gotcha.
Yes. Okay. So by these relations, let's say without complications that one is able to deal with, are very important because they tell us how to relate a transport and a flow property, and this means how to parameterize a model. Like in the dispersion principle, this is so fantastic because it's fully constrained by geometry and by hydrodynamics. And here we have something similar. And same as before when we talked about trapping times, now breakthrough times are simply sums of advection times in this case. This is the correlation length of our flow field. These are the flow velocities, the statistics we have determined. Then we can determine the distribution of these times from the velocity distribution. This is simply a mapping of random variables. And then, as an example, if you have a gamma type velocity distribution, you obtain, so in this case the alphas and betas are correct. You obtain, so if you have a velocity distribution that is tailed towards low velocities, you obtain transit times that are tailed towards high transit times, because they're inversely proportional. And in the same way, from a broad distribution of velocities, you can obtain breakthrough curves that have a power law. So now we have discussed two mechanisms that invalidate the dispersion principle. One is trapping due to diffusive mechanism, and another one is broad distributions of transit times due to advection. And so now observation. Transport times are broadly distributed. Particle velocities do not describe in general a temporal Markov process, but changing the point of view, we can have a spatial Markov process. This is how these type of processes are often called. And this principle seems to be valid also across scales, because the mechanisms, they are very similar. The mechanisms is, I have a flow field. The flow field is varying on a certain length scale. And this length scale can be tens of micrometers, or can be meters, or can be kilometers. And so now we have to finish. So the way to formalize that is the continuous sum random walk framework. So we have to go a little bit fast now. But these equations we have already seen. Very fundamental, very easy. It's just a regression relation. You identify a characteristic length scale, you advance the particles accordingly. Then you have to keep track of the time. When you know that you have a random advection problem, these transition times are given by the velocities, the velocity distribution. If you know that you have a trapping problem, these transition times are given by an advection time and the sum over the trapping events that you have. So this is it. So with this, you can already program a little simulation tool for particle tracking. These particle tracking algorithms are very, let's say from a conceptual point of view, easy. But this is sufficient to have an upscaled model for random advection and including matrix diffusion or trapping in low velocities. So now one can formalize this in the CTRW framework. So in this framework we have to think, what is now the particle position x of t? Because this does not give us x of t, it gives us particle position after n steps. But after n steps the time is a random object. So now what happens is, okay, x of t is equal to the position of the particle after n t steps. So now I have to think, okay, how many steps can a particle make at a given time t if time is made up of a sum of random transitions? So this nt is in principle the maximum number of steps such that the transition time is just smaller than your observation time. You have to think a little bit later. But it's the idea, no? So these concepts are not our usual way of thinking, so one has to get used to it. And this NT is a renewal process. It's called a renewal process. No? It counts a number of events that are separated by random times of a process that occurs until a certain time t. No? So it's actually something that you know from everyday life. No, not anymore, because now nobody's queuing up for train tickets, for example, anymore. No, because you buy everything online. But before you had to go to a counter, and then you can look and say how many people arrive at the counter in 1 hour. No, that's a random process because people, they don't occur at constant time increments. But typically you can describe it by a Poisson process. You can say that the arrival times of people is exponentially distributed, and this is the fundament of what is called queuing processes. No? It's these renewal times. And so now, if the waiting time between events is exponentially distributed, now exponential distribution is synonymous with a memory-less process. So why is that? Now, if we think, what is the waiting time until an event, if no event has occurred until a certain time t? No? So you're waiting for something to happen. You wait and you wait, and you say, nothing has happened in the last hour. No? So what is the expected time that I still have to wait until, I don't know, package arrives or something? No? So then if we have an exponential distribution of this in the event times, no, the probability that the time to wait is larger than the time I'm at now, given that nothing has happened until, I don't know, 1 hour ago. No, it's simply, this is the probability that nothing is going to happen, and this is the probability that nothing has happened until time capital T. No? It's the Bayes theorem. No? Conditional probability is probability divided by the probability of the conditional event, and then you see it's an exponential distribution. Nothing happens. Now I don't have to despair. But if you have a power law distribution, it's a fun fact. The longer you wait, the less unlikely it is that it happens. Yeah? Okay, because when I look at this probability for something to happen, if nothing has happened until the time t, then the probability actually decreases. No? So if this time t increases, now the longer nothing has occurred, the smaller the probability that actually something will happen. No? I mean, psychologically, I'm sure you have made this experience. No? But okay, with these renewal processes, we can now write down particle distributions. So I think we have to go a little bit faster now. But one can, let's say, with relatively elementary mathematics, can write down the distribution of particles, P of x and t, is now the sum, well, let's not go into details. No? So we can go through this. We can, let's go through it fast. We can come up with 2 equations. So when you go through the CTRW literature, oftentimes you see the starting point of it is this equation and that equation. They have an easy interpretation. I wanted to show you the steps, how to get there, but I think we have no time. But what you get is a distribution that the particle is at a position x at time t, is the probability r that the particle arrives at x at some earlier time, t minus t prime, and it waits there at this position until the time t. This is the probability that the waiting time at this position is t minus t prime. Now, this is the interpretation of this formula. And then we have an equation for the distribution of these arrival times. No? So the probability that the particle arrives at x at time t is the probability that it arrives at a previous time, at a different position, and it makes a transition both in space and time. Yeah, so if we had more time, we would see that the whole mathematical development is totally analogous to what we have seen for dispersion. Yeah? but with an additional complexity, which is that we now have not only an integral in space, but also an integral in time, and this is what gives what is called memory. No? And we can do very similar development as what we had done before. We can, let's go, we have, so now this is as far as we can get without using, let's say, with elementary calculus. Now, in order to treat these equations further, one needs to use Laplace transforms, which we are not going to do. But one can come up with an equation that is very similar to the advection-dispersion equation we had before. But we have now memory kernels, no? Because the fluxes at a given time, they are related to fluxes or to to states of our transport system at earlier times. Now, we have a broad distribution of timescales. No? So clearly, now when you think about matrix diffusion, the concentration of that you measure at an outlet is due to solute particles or solute that maybe enter the matrix, spend there a long time, and then exits. No? So this particle has a very long history. Yeah, so it has a very long memory of things that it has seen on the way. This is the meaning of these memory terms. No? And then this memory, so there is a memory kernel that you can parameterize with the distribution of flow velocities, for example, or with the distribution of trapping and residence times. And then, let's say this is a longer calculation to show that the same CTRW framework also reduces to an equation in which, so this is, I don't know whether some of you is familiar with that, but there is this mobile immobile or multirate mass transfer transport theory, and the equations are given by that. No? So you have a mobile concentration, you have an exchange with an immobile mass, which is quantified by a memory function, and then you have the flux in the mobile phase. So this could be fracture transport, M would be fracture concentration, and this is exchange with the matrix, for example. Yeah? And with this, that's a summary. So particle speeds evolve on a characteristic length scale. This would be a general principle that helps us to upscale. And we have broad distributions of trapping and transition times. So now parameterization is something very important, because this type of modeling approaches, they have been highly criticized because one needed to fit many behaviors. No? For example, you fit an exponent, or you fit a length scale, or you fit a time scale. And it has been criticized maybe 10, 20 years ago, no? To say, you have a nice theory, you have 4 fitting parameters, of course you can fit anything. No? But these models, they are parameterizable by flow properties and by geometry, just like in the framework of the dispersion principle. Yeah? And now I think probably I have to stop now. No? Yes. So I have now, there is a series of applications of this theory. Let's take maybe 5 more minutes, or not. Because I mean, you can look at it in the presentation after, but well, maybe we go quick. Because pore to regional scale, no, it's really quick. So what did we do? We did a simulation, Stokes equation in 3D pore space. We calculated the velocity PDFs. We parameterized the CTRW model. We look at breakthrough curves, and the symbols is what we measured from the direct numerical simulations, and the solid lines is what we obtained from the CTRW model that we parameterize. We parameterize it with the velocity PDF. That's a lot of information, but it's not a transport attribute. It's a flow attribute. No? So this works. Next was, so this was pore scale. Then we go to Darcy scale, do numerical simulation. This was 2D, works in 3D similarly. So we determined the PDF of flow velocities. And in this case, we looked at the CTRW predictions For the width of a solute plume and for the concentration profile, again, symbols is the direct simulation, and the lines would be the prediction of this upscaled model. And for fractured media, similarly, but I think that Philip is probably showing a counter example. Yeah, exactly. But this is what we got with DFN works. It's breakthrough curves. And this was an example for the to model the MADE experiment. So what we did here is we went through the literature and we found detailed characterization of the hydraulic conductivity distribution. There has been a lot of work and is still work ongoing. Well, we took the K distribution, we solved for the Darcy flow, and we used the flow results to model the integrated plumes at the MADE side, and so we make a relatively good characterization. Now we correctly characterize the peaks that you have due to retention at the injection point and the forward tail. So we test this theory against numerical simulations and against the experimental data. No? And this is also a way we always have to challenge these models in order to see are they really valid, or do we have to extend them, or is there some physics we are missing? And that's it.
Thanks a lot. Maybe just one very quick question, and then I think we have to continue. Oh, we have to go to the coffee break actually. Who has a very quick question?
So, very nice presentation, thanks. So from the equation you showed for the trapping time, it does not depend on the diffusion coefficient or characteristic length, but
which one?
For the trapping time.
Yeah, okay, well, let me see.
But in the definition you said it depends on the diffusion of the wall. Am I right?
Yeah.
So can you explain it again?
I said, look, it depends on diffusion. This was, okay, residence time. Right? This one is
the residence time?
Exactly, yes. So you see?
Trapping
time too, I just left it out. No, it depends. So this is T divided by tau D.
Okay,
yeah?
okay.
No, but this is oftentimes done. You just put a proportionality to the behavior that you find remarkable. And here it's the power law. But of course, the details, they depend on the diffusion coefficient.
So what's the definition of the trapping time?
Of the trapping time is, so fracture channel matrix. So now you have a solute transported through. Let's conceptualize it with a solute particle. So and then by diffusion it can get close to the interface between matrix and fracture, and then it's going to enter the matrix. No? So it's going to diffuse in the matrix, and now the moment it enters, you put the counter on. No? So because it's trapped. So then it can diffuse around, and then eventually it's going to exit. No? So the time between the entry and the exit, this is the trapping time. And the same on the pore scale. No? I've put this example that you have these dead-end pores. So here the same. So particles move along the pore channel, and eventually by diffusion they can go, by diffusion or sometimes advection, they can go into a dead-end pore, and the same thing you measure between the entry and the exit. So that's a trapping time. Yeah.
Okay, then let's thank the speaker again.